Hey Ramblers, this video is going to cover the last part of section 1.6 or chapter 1.6 in our book, and it deals with the last in the library of functions that we're going to cover, and that is rational functions. Now rational functions, as you see, will be a ratio of two polynomial functions, which of course are kind of the sum of power functions. So all three are really closely related. As we talk about rational functions, it's a good time to bring up end behavior, again, as we saw in the first half, and also talk about things like horizontal asymptotes and vertical asymptotes. The last thing we'll want to do is do a quick example of how to get an idea of what a rational function looks like. How can we identify what the what the vertical asymptotes are, what the horizontal asymptotes are, what the x and the y intercepts are. It just gives us a sense of what the graph looks like. So please take careful notes on this, pause often, and thanks for watching. Rational functions are just a ratio of polynomials. So we could have an example like f of x equals x squared plus 7x plus 12 over x squared minus 4. And that would be a polynomial function. That would be a rational function because both of these in the numerator and in the denominator are polynomials. Okay, the reason we spend a lot of time talking about rational functions is, well, they're part of the library of functions, but also they bring up two important topics, horizontal asymptotes and vertical asymptotes. So let's define what those are. A horizontal asymptote is a horizontal line like y equals L that f of x approaches as x approaches either positive infinity or x approaches negative infinity. Now we're going to meet in not the next section but in the end of the chapter. We're going to recognize that this is a limit, which is why we're referring it to L as L. So what this means is that you can have a function, and here's your x-axis and your y-axis, and if you have some horizontal line called L that the function is approaching as x goes out toward infinity, then that would be considered a horizontal asymptote. Okay, let's look at a vertical asymptote. A vertical asymptote is a vertical line, let's say call it x equals k, such that as x approaches k from either side, so we could say from the positive or the negative side in parentheses, f of x is going toward either positive infinity or f of x goes toward negative infinity. So let's get a picture of what that looks like. You have a graph, and there's your x-axis and your y-axis, and you could have some vertical line that we'll call k, and that would serve as a vertical asymptote if the function approaches infinity as x gets closer to that line, x equals k. All right, those are two really important definitions. Make sure they're in your notes. And now let's take a look at how we find some of the key parts of a function so that we can graph it. Okay, the example I want to look at is example number 4. It's also found on page 49 in your book if you need more detail on the explanation in there. But they want us to look at a graph and explain the behavior of y equals 3x squared minus 12 divided by the quantity x squared minus 1. And so to do that, we have to break it into kind of certain steps. The first thing I think we're going to want to talk about are the x-intercepts and the y-intercepts. And then we'll also want to identify what the horizontal asymptotes are and the vertical asymptotes. So let's talk about each one of these and how to find them. To get the x-intercepts, well, if you look at a graph, the graph of any function, the x-intercept is the value of the function when y equals 0. So to do that, we're going to set this function equal to 0. So 0 would equal 3 times x plus 2 times x minus 2 divided by x plus 1 times x minus 1. Now think about it. If this function is 0 here, that has to be the values where the numerator is equal to 0. That's going to happen when x equals negative 2 or when x equals positive 2, which would make these two factors equal to 0 when we plugged in either of those two x values. So the x-intercepts are going to be at negative 2 and positive 2. The y-intercept can be found in a similar fashion. But here, you'll notice on the axis I've drawn, the y-intercept is the value when x equals 0. So I'm going to simply look at the y-intercept equals 3 times 0 plus 2 times 0 minus 2 divided by 0 plus 1 times 0 minus 1, which gives us negative 12 divided by negative 1, which is just 12. So our y-intercept is equal to 12. Our x-intercepts are positive and negative 2, which leaves us to the horizontal asymptote and the vertical asymptote. Vertical asymptote is found by anything that makes the denominator equal to 0. So vertical asymptote would be anywhere where x is equal to positive or negative 1, because that would make the denominator equal to 0. And to find the horizontal asymptote, we're just going to look at the end behavior of this model. The end behavior of this function. Now think about it. This was 3x squared over x squared minus 1. As we saw in the previous video, the 12 and the negative 1 are going to have absolutely no impact on this graph out at infinity. The example we looked at in the last video, there wasn't much of a difference between the power function and the polynomial function once we were past x equals 20 or so. So this is really going to look like 3x squared over x. And that's going to simplify to y equals 3. So what's the shortcut? Well, to find the horizontal asymptote of a rational function, you just take you take a look at the lead term. Okay, so here's the step when you're sketching a rational function. To find the intercepts, x-intercept is just the x's that make the numerator equal to 0. So factor the numerator and set it equal to 0. To find the y-intercepts, you just find the value of the function when you plug in 0 for x. The vertical asymptotes are found by the x values that make the denominator equal to 0. So in the same way you find the x-intercept, but instead of factoring the numerator, factor the denominator, set it equal to 0. And then here's the important part that I didn't have room to type, so write this down. Horizontal asymptotes are found by comparing the lead terms. If the numerator has a lead term that has a higher exponent, then there is no horizontal asymptote. If the denominator's lead term has a higher exponent, then the horizontal asymptote is 0. And if the top and bottom have the same exponent, you compare the ratio of coefficients. All right, normally I'd write that out, but I know this is all review from last year. So Ramblers, make sure you've got the notes down on this. These are tricks that really work for rational functions, not for everything else, so don't overgeneralize it. We'll have some more practice with the exercises. Okay, thanks for watching.